Module 3, Topic 2, Lesson 1 notes. First, among equals. We're on page 1, reasoning with equal expressions. So we are taking the two expressions, or expressions that we've been working with, and we are setting them equal to each other to form equations. Remember, an expression does not have an equal sign, an equation does. An equation is a statement of equality between two expressions. An equation can contain number, variable, or both in the same mathematical sentence. Consider the equation 8 plus 4 equals something plus 5. It has an unknown number. One way to determine the unknown number is to rewrite the expressions on both sides of the equal sign until they match. Consider each reasoning strategy that is used to determine the unknown number in 8 plus 4 equals something plus 5. As we know what this is, 8 plus 4 is 12. So we need to figure out what number plus 5 will give us the same answer. Your number is 7. 7 plus 5 is 12. But how can we do that? How can we make this work when we don't know the math problem right away? This is what we're going to look at. So let's take a look at Riley's. Riley is wrong in her thinking. And we want to figure out why that is. She says the equal sign tells me to perform the operation on the left in the equation 8 plus 4. Well, that's all good and well, but that 12 does not become part of our other equation on the other side. If you look at hers, you say 8 plus 4 equals 12 plus 5. That's not a true statement. This is 12 and this is 17. Well, 17 is not our missing number. And then she goes on to say, like, this isn't even what she has down. She says, now that I have this 12, I'm going to take 12 plus 5, and I'm going to add that together. So actually, my missing number is 17. So she just did one long math problem. So if we take her number, this is what we have to do to prove it, we have to plug it back into our original equation. Equals 17 plus 5. Well, that's not true. 12 is not equal to, what is this, 22? That's not right at all. So how do we do this so it is correct? What are they trying to get us to do with these equal equations? Let's take a look at Clover's and Fiona's. Clover says, I can determine the unknown number in 8 plus 4 is equal to something plus 5 by rewriting the expression on the left. I can take 1 from 8 and give it to 4 and keep the value of the expression the same. Okay, so all she is doing is she sees a 5 on the right-hand side. She's like, well, I know that I can make 4 into 5 by adding 1. But we can't just add 1 to my equation. My two numbers, or whatever I'm adding over here, always has to equal 12. So if I want that to happen, I'm going to turn my problem into 5 plus 7. I'm going to subtract 1 from 8, and I'm going to add that 1 to the 4. And now I have 7 plus 5. Well, look at this. 5. My missing number is 7. Is 12 equal to 12? Absolutely. Okay, now we're going to look at Fiona's. Fiona says, I can determine the unknown number in 8 plus 4 equals something plus 5 by rewriting both expressions. She does the same thing, except she breaks it down a little bit more. She takes her 5 and she turns it into 4 plus 1. So she's got the 4 on both sides. Then she knows that she can take this 8, and she can break it into 7 plus 1. So remember, this was the 5 that got broken into 1 plus 4. And this 8 got split into 7 plus 1. Now look at this. 7 plus 1 plus 4. Well, I've got the 1 and the 4. I'm just missing the 7. How Are their strategies similar? Take a look at number 2. How are Clover and Fiona's strategies similar? They both rewrote the equations, or expressions, I should say, until they were the same on both sides. So that's what we're going to do. You're going to have 3 opportunities to try this. I'll do 1 more with you, and then you're going to do 2 on your own. Turn to page 2. We have 31 plus 67 equals something plus 12. Make sure you show your work on all of this. So I want to turn this 67 into 12. So in order to do that, I need to see 12 plus what equals 67. So 67 minus 12 equals, it's 15. 55. That was silly. 55. So that means I have to subtract 55 from 67. Okay? So this is what it'll look like. 67 minus 55. But I can't just leave that hanging out there. So I'm going to add it to 31. So 31 plus 55 is 86 plus, this is now 12, equals something plus 12. They're the same now, 86. Not 86 plus, yeah, 86. But let's see if that's true. We're going to take this and we're going to plug it back into our missing number here, okay? So if I take 31 plus 67 equals 86 plus 12, these should be the same. I get 98, and I get 98. This is a true statement. I want you to pause the video and do A and B. Do that now. All right, here's what I came up with. A, I did it just like we did on top. B, I changed a different number. I don't need the parentheses there. I'm just going to fix that. It just needs to be 18. I knew that I could add 5 to 9 to get 14. So rather than making it look exactly like it, if you notice this says 14 plus 18 equals 18 plus 14. But because of the commutative property, I can flip these around and they still equal the same thing. Okay? Next page. Now we're going to talk about equations. Equations come in many forms because expressions are either numeric or algebraic. Equations can be made of just numbers or both numbers and variables. Equations are statements. They're like number sentences. They may be always true, never true, or true for only one or more values of the variable. So that just means, if you look here, if they tell you what x is, rather than saying to try any number of values for x, they just say x equals 5. So this statement is true if x is 5 all the time. Okay? First spelling mistake I found. Oh, and I found this one too. I need an extra space here. So it looks like this. Always true. X equals x. 6 will always equal 6, no matter what. This one, if I put 10 in for x, 10 will never equal 12. It's never going to happen. And then this is just sometimes true or true only for certain values. So x equals 5. Okay, so if I put 5 in, 5 plus 2 is 7, 7 equals 7. This will always be true if x equals 5. So a solution to an equation is any value for a variable that makes the equation true. Use the set of expressions on the left to create 5 different equations. Use the solution set 0. So when they talk about solution sets, they're going to put them in these funny little parentheses. And that just says use these numbers to try to solve it, to determine if your equations are always true or never true. After I made this, I realized this doesn't make much sense. If you want it to be sometimes true, you have to find the value that makes that statement true. Kind of like this, where I say x equals 5. So you can skip this one if you would like to. If you want to try it, then you find the value that makes each of your expressions or equations true. Now, you are going to match these up any way you want. They don't have to make sense. You're just going to write two expressions, setting them equal to each other. For instance, I'm going to say 6 minus 2 equals x. Okay? I'm going to set these two equal together. Then I'm going to go 2x equals, let's go 0. And then I want, let's do 3x equal to 2x. Okay? And then let's try a big one. Let's do 2 times x plus 1 and 2x plus 2. Okay? 5 is yours. So you're going to do that all on your own, and I'm going to check it on Tuesday. Page, whatever we're on, number 5 is your responsibility. I gotta see what page we're on. Hang on. Page 3. Page 3, number 5, your responsibility. Okay, now I've got to take 0, and plug it in. So 6 minus 2 is 4 equals 0, never true. Put 0 in, 0 equals 0, that's always true. Plug in 0 here, 0, so 3 times 0, x is 0. X is 0, always true. This is 0 and this is 0. This is 0 plus 1 is 1. 1 times 2 is 2. 2 times 0 is 0. 0 plus 2 is, what do you know? Look at that. Worked. Always true. Your job is to do number 5. Okay? Remember, you can always pause the video and go back. Page 4. Now we're going to talk about inequalities. You guys know what inequalities are, the greater than and the less than. Remember, less than spells the word less. I want you to take a look at these two graphs. Letter A asks, what are the differences or what are the similarities? What's going on with them? And how does this one's graph make sense? Well, if you look at it, x is greater than 3. That means all numbers larger than 3 will make it true. Larger than 3. You can't say 3. 3 is not, if I did this, 3 is greater than 3, not true. It has to be larger than 3. This one, now we've got this little funny thing underneath it. It just means greater than or equal to. And this just states that greater than or equal to 3, 3 and all numbers larger make it true. So I could write in here 3 is greater than or equal to 3, check, true story. 4 greater than or equal to 3, true story. Okay? And if you notice, they're done differently. This one with just the greater than, it's an open circle. Right here. That just means 3 is not included in the solution. The closed circle means 3 is included. I want you to turn to page 5 and see if you can finish this one. It's the same thing, just less than or equal to. So page 5, number 2, checking on that one. So pause the video and complete that. All right, now we're going to do some practice with it. We're going to write an inequality. So you start with x. All of them are going to start with x, and they're going to have this number that it starts at on it. But now I have to decide, is it open or closed? Well, it's closed, so it's going to be equal to. And now I've got to make the sentence true. X is 14 is less than 15. Okay? Because all of these make it true. 14 is less than or equal to 15. And it's closed, so that means 15 can make it true as well. Go down to letter D. This one's a little trickier. D has it go in both directions, so X. And all this says is that X cannot equal 23. It can be all of these numbers, left or right, but it cannot equal 23. You are in charge of B and C. So page 6, B and C. Pause the video and do that now. Now we're going to graph. So first we look at where am I going to start my graph? 14. So I'm going to start with just a circle. It has the equals to underneath, so I have to shade it in. And now any number that is less than 14 makes this true. So which direction am I going to go? Am I going to shade up here? Well, these numbers up here are not less than 14. So I'm going to shade this direction. And yes, this is how I show my shading. Okay. Let's try letter C. C is a little trickier. It's a little backwards. I'm going to rewrite it so it's a mirror image. So I'm going to look at it right to left, okay? X is greater than or equal to 2.5. And notice how I said mirror image. If I were to fold this in half, they would match up. So same thing. I'm going to go to 2.5, and I'm going to make an open circle for now. This has the equals to, so I can fill it in. And it says all numbers that are greater than x. So it has to be any number that is greater than 2.5. So I go this way. Your job is page 7, B, D, and E. Okay. Last page, page 8. I don't have it on here. This is page 8. We're going to write and graph now. So it's always going to be x. You're going to use the number they give you, 2,900. But now we got to figure out the maximum load. So that means the largest number can be 2,900. So that means x has to be smaller or equal to. So I'm going to put a dot here. I'm going to do 2,900. And I'm going to show everything this direction. Okay? A car seat can seat up to 8 passengers. So x, 8, up to, I can't go over 8, so x has to be less than, but I can have 8, so it's equal. Closed, 8, doot. All right, you are in charge of C and D. Okay, that is it. Good luck. Do your best. I have these typed up in It's Learning. Okay?